Hello everyone, and welcome to this Genetic Engineering and Biotechnology News webinar. It's entitled Quantifying Stability and Determining Aggregation Pathways for Biologics. Ensuring bioproduct stability is one of the most critical aspects of new therapeutic development and commercialization. The focus on stability and identifying the conditions that maximize the stability of a biologic requires exquisite attention to the processes of purification, formulation, and storage. Today's GEN webinar will discuss methods and results using chemical denaturation for measuring biologic stability in a given formulation. In addition, we'll take a close look at an innovative system that provides quantitative data on protein stability. It allows researchers to rank protein constructs, screen and optimize formulations, and assess the propensity for denaturation and aggregation. I'm John Sterling, Editor-in-Chief of GEN, and I'm going to serve as moderator. But first, let's meet our webinar presenters. Dr. Joe Barco is Senior Product Manager at Unchained Labs. Dr. Barco will briefly discuss the HUNK, a novel automated chemical denaturation platform. Dr. Catherine Bowers serves as Principal Scientist at FUJIFILM Diosynth Biotechnologies. Dr. Bowers will present chemical denaturation data and its application to stability determination for protein comparability and for formulation optimization. After the panelists make their presentations, there will be a question and answer period. Feel free to send in a question for our panelists at any time during the webinar. Type your questions into the Ask a Question box on the lower left of your console and then hit Submit. The panel will try to answer as many questions as possible. So if everyone's ready, let's get going. Dr. Joe Barco will be our lead-off presenter. Joe, the floor is all yours.
Thank you, John, and thank you all for joining us this morning. My name is Joe Barco, and I'm the Senior Product Manager at Unchained Labs. I'd like to talk to you first today a little bit about Unchained Labs, and then talk to you about the HUNK. Unchained Labs is a new company. We're less than a year old. We have 50 employees in 4 offices, and we are a venture capital-backed private company. So far, we have 100 customers. You may be asking yourself, how does a 1-year-old company have 100 customers already? And it really comes down to our business model. What Unchained Labs has done is we've acquired 3 smaller companies that have products already developed and on the market. Our intent is to work more efficiently with those products and with a common sales force, engineering staff, and support team to help make those products better, as well as to develop our own products going forward. What about the name Unchained Labs? The idea behind the name is that biologic stability labs are trying to break free from something, and that is using tools that are not designed to do what you need it to do. The problem with a lot of instruments on the market right now is they're doing something that they were not designed to do. A lot of instrumentation has been developed around small molecule work. So in a protein formulations lab, that instrument is not doing what you need it to do. You'll eventually get the answer you need, but it may take a lot of work to get there, and it may not be as elegant as if the product was designed with your needs in mind. And that is our goal behind Unchained Labs, to help scientists develop better biologics. We currently have 3 instruments to help scientists do this. The tool on the left is called the unit, which is a simultaneous TM and TAG measurement system. The tool on the right is a sizing system, the HUNK, which does DLS on as little as 5 microliters a sample. And the instrument in the middle is called the HUNK, which does prediction. I should be more specific about what we mean by prediction, and that's stability prediction. Now, you do not have a tool that currently does this in your lab, so let me tell you what the HUNK does a little bit more. So the HUNK predicts stability by measuring delta G. We also have a current new process called delta G trend, which is a way to use the HUNK to predict aggregation. Many of you have not used or encountered delta G since maybe sophomore year of college. So we're not going to do a thermodynamics lecture today. What we're going to do is focus on what the instrument does and what information that helps you gather for your protein. The only real equation we're going to have to remember is this one, which is delta G equals minus RT ln K. How does this equation apply to biologics? For any protein in any formulation at any temperature, it exists in equilibrium between a folded, native state and a denatured state. Of course, for better biologics, most of the equilibrium is toward the left or the native folded structures. What the HUNK does is it automates the delta G measurement. Protein and formulations go in. The instrument does all of the plate generation and reads the plate and gives you a chemical denaturation curve. Think of chemical denaturation as a chemical ramp to unfold the protein or force a protein into an unfolded state. The concept behind the HUNK is to automate the chemical denaturation process. The steps of denaturation are to add proteins and formulations, and they go in the application-specific tray. You need to generate assay curves or denaturation curves, so that goes in plates that are stored in the stacker. You need liquid handling to make your plates, and you need some way to read the plate. So these are all enclosed in one system. It works with scheduling software that's developed proprietary to the HUNK to ensure that your sample measurements are robust. Here's an example of one tray that is used for formulation screening. In the front are two 96-well blocks that would contain your formulations and your denaturant. In the back are vials of protein that would be chilled to the temperature suggested by the end user. After your tray is loaded, it simply goes into the drawer of the instrument. The experimenter loads their stacks full of empty plates that will be their assay plates. And inside the machine, we see the tray. We see a stage where the assay plate is going to be made, and the liquid handling sections in the formulator and the wash station. The system is designed to be automated and hands-off. Once you set up your program, you leave. The HUNK will make your assay plates. When it's time to read the plate, it will move the plate into position below the fluorescent zipper tip. What it will do is generate a series of chemical denaturation curves depending on the experiment the operator is doing. This particular example shows how we're getting a delta G measurement. The protein is denaturing with increasing amounts of denaturant. At a certain concentration, labeled here as a C1/2, half of the protein is folded and half of it isn't denatured. At that point, the C1/2 concentration times the slope is equal to delta G. To do denaturation curves on the HUNK, you require very little protein. This particular example is 3 micrograms per mil of a monoclonal antibody. And we still can see a signal and change in denaturant concentration causing a shift in fluorescence. It's also reliable and reproducible. If we take the same monoclonal antibody, measure it 12 separate times, we get 12 overlapping curves and delta G measurements within 0.1 kilocalorie of one another. As you can see from this example, it can also track multiple transitions. So this particular example has 2 transitions in the unfolding process. To learn the most out of your delta G measurements, you need a precise instrumentation that can do that. Very small changes in delta G, such as 1.4 kilocalories per mole, signify a 10-fold change in the amount of denatured protein. You can see from this table that higher delta Gs are better because you'd have more native folded protein and less denatured protein. Delta G measurements can give a series of insights into any sort of application where you need to understand protein stability. These could be examples like looking and comparing protein constructs, formulation screening and optimization, and also setting up information and the best formulations for long-term stability. Protein aggregation is, of course, a big concern in understanding long-term stability. It affects shelf life. It affects what happens after the drug goes to a patient. It affects potency. It affects possibly immunogenic responses. Of course, there's a reputation issue to be concerned about if a product needs to be recalled because of aggregation or particulates. So wouldn't this be nice, that it was just this simple, that you could take a protein in formulation and know on day 1 whether or not that protein was going to aggregate? This brings us back to our concept of using the right tool for the job. SEC measurements take a long time. You do not know whether a protein is going to aggregate possibly for up to a year afterwards. And if it is aggregating, you don't know how it's aggregating. You don't know if it's aggregating from native state or denatured state aggregation. What the HUNK can do in one day is predict if a protein is going to aggregate, and if so, what is the aggregation pathway. Illustrated here is this concept which we call delta G trend. What it means is that if we monitor changes in delta G with increasing protein concentrations, we can get a sense of whether or not the protein is aggregating and the pathway of aggregation. If you have no change in delta G as your protein concentration is increasing, that's shown here in the green line, that means you have no aggregation occurring. If you have an increase in delta G as increasing protein concentration, that is aggregation occurring from the native state of the protein. If you have a decreasing delta G with increasing protein concentration, that's shown in the red line, that is aggregation from the denatured state. The math and the equations behind this are illustrated in this paper in collaboration between Ernesto Freire and Unchained Labs. Catherine will talk more about this in her part of the presentation. What I hope I've given you is a sense of how using the right tool for the right job is a much more elegant and straightforward solution than trying to use tools that are not designed for your process. Thank you, and with that, I'd like to turn it back to John.
Thank you, Joe, for that very detailed description and presentation on the HUNK. It was very clear and precise and very much appreciated. Thank you. If you're just now joining our webinar, a big welcome. Just a reminder that there will be a question and answer segment after the last presentation. Type your question into the box on the lower left of your console and then hit submit. Our next speaker will be Dr. Catherine Bowers, and Catherine, the floor is going to be all yours.
Hello, everyone. Thank you so much for joining us today for this webinar centered around isothermal chemical denaturation. Today, I'd like to just share some data with you that has been collected at our organization and give you an idea of how we use ICD as a key biophysical assay in a contract research environment. So if you have never heard of Diosynth Biotechnologies, we are part of the FUJIFILM Global Corporation. We are a CRO, CMO business that helps people bring their protein biologics to the market, to the clinic and the market. We have 3 locations, 2 in the United States, in North Carolina and Texas, and 1 location in the UK in Billingham. We have a lot of experience with proteins, developing over 230 molecules and processes. We have an extensive successful inspection history. We've been at this a while, and we have about 1,100 people strong. I want to focus not so much on the manufacturing part of our business, but more on the analytical solution part of our business. Listed on this slide is just a series of analytical services that we offer at FUJIFILM, and you know, it's very broad, from pre-formulation development all the way through method lifecycle management. My area of focus is more to the left of the slide. I'm definitely highly involved in pre-formulation and formulation development, as well as supporting our process development folks in coming up with robust ways to purify and stabilize protein molecules. As a formulation scientist and also involved in protein biophysical characterization, I have many roles. Again, as I was saying earlier, formulation development, pre-formulation development, but also involved in analytical assay development and troubleshooting, post-scale-up manufacturing support, process development support. With all of these roles, you can imagine that we're very busy. So we need assays that are relevant to the problem, are flexible, meaning that they'll work for any class of protein. They have to be robust in that we can't continue to repeat experiments. They have to give us good, right, solid answers from the beginning. They have to be information-rich and universal. I always like to make this statement that it's really important to use a comprehensive analytical panel during the development process of your proteins. you don't want to focus too heavily on one method. You want to look at your protein development very holistically, looking at purity, stability, functionality, heterogeneity, and higher order structure. Having this type of package will provide an information-rich data package that you can actually leverage during the development from beginning to end to form stable and efficacious therapeutics. In our labs at FUJIFILM, we have quite a number of analytical and biophysical techniques that we leverage to create these data sets when we're in a development project. I really believe that the success of the biotherapeutic development program is directly linked to the capabilities of your analytical and biophysical toolbox. So today I'm going to focus on isothermal chemical denaturation, or I'll state it as ICD going forward, but you also have to think about all of these other aspects of your molecule too, and this just highlights some of the methods that we use in-house. As I was stating earlier, we have to have methods that are flexible and universal. And the reason for that, as a contract service provider, we work with all kinds of proteins. And I really do think it is the joy of variety as a scientist. We've worked on, antibodies, but also enzymes and cytokines and virus-like particles, which are huge. So having this type of variety requires that we have methods that really are universal. So putting the pieces together, we have to realize that everything that we do in the manufacturing of a protein can impact its stability, starting from early expression all the way to storage and everything in between. All of these factors that impact protein stability have to be monitored and controlled in a manner that maximizes the quality and the stability of the protein therapeutic. What I'm going to talk to you about today, ICD, is one of those valuable assays that can be used to determine the impact of numerous stressors on the stability of the molecule, and thus guiding the overall development process. As I stated, because we have this huge variety of proteins that we work with, ICD is universal. So no matter what the form, proteins can be studied by ICD. And I just have some examples here of proteins that like to self-associate, or they aggregate, become unfolded, conjugated proteins, fusions, and really big and complex megadalton-sized proteins. So what does ICD measure? Joe went into this a little bit. I'm just going to take it into just a little bit more depth so you understand what we're actually doing, measuring, and what the calculations involve. So ICD measures the free energy difference between the native and the unfolded molecule. This is a direct measure of the inherent stability of the protein in its current state, whether that be a change in formulation, a mutation, whether it's been put under some kind of mechanical or chemical stress, all of those things. So when you unfold a protein, it is a dynamic equilibrium where you're going between states, but overall between the native and the unfolded state and everywhere in between. In the case of chemical denaturation, where you are in that equilibrium is highly dependent on your denaturant concentration. So you have, equilibrium constants from folded and to the unfolded state. The ratio of those, again, depending on your denaturant concentration, gives you your equilibrium constant KEQ. As Joe mentioned, delta G is equal to negative RT natural log of KEQ. So then how do we use that value? Well, let's first take a look at the output of an ICD experiment and illustrate how this data is used to understand protein stability. In the upper right-hand corner is a representation of a typical experiment performed using ICD, where you're looking at your fluorescence emission as a function of urea concentration. You see this nice unfolding curve, single transition. What the program actually does during fitting, it determines both the unfolded baseline and the native baseline. From those values, it calculates the fraction unfolded for your transition, and you can see the equation number 2. That fraction unfolded then gets translated into your equilibrium constant K, as you can see in equation 3. And finally, you tie it all together, and delta G equals RT natural log of K. So once you have those values in your transition for the different denaturant concentrations, you then do a linear extrapolation for the calculation of delta G in the absence of denaturant. At the midpoint of denaturation, where the fraction unfolded is 0.5, or 50%, the delta G is equal to 0. At this value, the concentration of denaturant is termed C1/2, and the slope is termed M, and this represents the cooperativity of the unfolding reaction, and it's related to the amount of hydrophobic surface that is exposed upon unfolding. So a steep slope equals higher cooperativity. Okay, so you say, I have these thermodynamic values. Well, what do they mean? For all of them, the delta G0 in the absence of denaturant, the C1/2, and the slope, as they transition to higher values, you can see that your protein is becoming more stable. Now, there is a balance because they all fit into that equation. So just because you have an increase in delta G, you may correspondingly have a change in your M value and so forth. So in and of themselves, higher numbers mean more stable, but again, they have to be taken in a holistic approach. So ICD in the past, how was this done before the automated system was available? Well, if you've ever done this, you first create all of your samples by hand, increasing concentrations or decreasing concentrations of denaturant, whether you're unfolding or refolding. You have to load each sample by hand into a cuvette. You have to put that cuvette into a spectrophotometer and read it, take the cuvette out, wash it, rinse, and repeat. And I say about a week later, and that really is the case, about a week later, especially if you have to repeat the data, you have your data, if you're lucky. How do I know this? The data that you see on the lower right-hand screen is actually data from graduate school for my thesis. So I do have first-hand experience in the pain and agony of doing ICD by hand. But what about now? With Unchained Labs ICD instrument, we now have freedom. We don't have to no longer do it by hand. We have efficiency. We load up our buffers and samples, and we hit go and come back, and we have lots of quality data. So let me share with you some examples of the utility of ICD at FUJIFILM Diosynth Biotechnologies. I'm going to show you 3 examples. The first example is a really straightforward, simple application of ICD, and this is screening buffers for a protein purification step. Protein purification, definitely a multi-step process. The protein is undergoing all kinds of changes in ionic strength, pH, buffer type, and then finally the UFDF process to make your final drug substance. You know, all proteins have unique characteristics, even if they're from the same family. For example, monoclonal antibodies. So even though maybe the chromatography steps, even the order might be the same, the buffer type, pH, concentration, and ionic strength could vary between that family of molecules to where for one monoclonal antibody, the buffer works just fine, and for another one, it absolutely does not like the buffer. This happens a lot in your post-capture step and viral inactivation. So we really need the ability to pre-screen buffer conditions and troubleshoot problematic steps in a given unit operation, and we'd like to do that as the development process is happening. So here is a straightforward application of ICD to screen buffers for a charge-based purification step. In this case, we use the auto formulation feature of the instrument to vary buffer concentration. Instead of using ionic strength to dilute the protein, the scientists decided that using sodium chloride, the scientists decided they would try to increase the buffer concentration. And the concern was is that as that buffer concentration was increased, that destabilization would occur. So we carried out a series of ICD titrations. The data on the left is the output of the fitted data. So you see the fraction denatured as a function of denaturant concentration, as well as a derivative of that. And that derivative helps to highlight the midpoint, or that C1/2 value. So when this data was fitted and plotted as a function of buffer concentration, the delta G, the M value, and the C1/2 value all increased as a function of buffer concentration. This indicated that increasing the buffer concentration did not destabilize the molecule, but actually had the opposite effect. So the scientists felt pretty confident going forward with that purification step using that process evolution. The second example is a little bit out of the box when it comes to doing ICD. This was a case where we were looking at a protein that was expressed in E. coli inclusion bodies. If you've ever worked with E. coli inclusion bodies, you know that they have to be treated with a high concentration of denaturant to actually remove the protein from the inclusion body and then refold the protein to take it through the purification to the final drug substance. Well, protein folding is very, very complex, and unfortunately misfolding is a common occurrence even with the most simple of proteins, single domain proteins, small proteins. What I'm showing on the left is just what we call the folding landscape, basically, as the unfolded protein proceeds down the energy funnel to the folded protein. You can kind of see there's a lot of places where things can go wrong. In practical terms, when we're doing this in the lab, it's kind of like a black box. We're not really able to see what's happening with the protein as it refolds and where we can intervene when things don't go right. I'm going to show you an example of a fusion protein. Two separate proteins separated by a linker. Each protein, domain A and domain B, have an intermolecular disulfide bond that needs to be correctly formed. So some of the important factors during this process are going to be, what does my solubilization buffer contain? Do I have a reductant in there to help with the disulfides? And my refolding buffer, it's the same thing. I want to correctly form these disulfide bonds, so something's going to have to be in there to help it. How am I going to refold? Am I going to do slow or fast dilution, or am I going to do on-column refolding? And then temperature is going to be an issue. Today's example is going to focus on the buffers themselves and the impact that they have on the refolding of this molecule. So how to peer into the black box. When I first started working with the automated ICD instrument, this was one of the first experiments that I wanted to do because at the time, this was a real-life problem going on in our company. We had a protein, and the yields after refolding were terrible, and we had to figure out how we could improve that. So we can monitor unfolding and refolding of a target protein using ICD. And of course, we're using the fluorescence-based method from Unchained Labs. So on the right is actual data from unfolding of this protein in formulation buffer. So as it sits in its native state, treated with increasing concentrations of guanidine and watching it unfold. The lines here are not a fit. They're for illustrative purposes only. I just want to make that clear. If you're familiar with chemical denaturation, a lot of times you see a single transition, a nice smooth transition from the native state to the unfolded state. With this particular protein, especially with it being a two-domain fusion protein, we actually have a three-state unfolding reaction where we're going through an intermediate. So we have a transition from N to I and from I to U. So we're going to actually be monitoring both of those and the impact of buffers on those transitions. So the first thing we had to do is understand the protein in its native state and the impact of those solubilization and refold buffers on the refolding of the molecule. In the upper panel is shown the unfolding of this fusion protein in formulation buffer versus solubilization buffer, which contains DTT, which is the reducing agent. In the red is what data I had shown previously, where we see nice three-state transition. But look what happens when we add a reducing agent. The unfolding of the molecule now shows that that second transition from I to U is clearly destabilized, meaning that the addition of DTT, the reduction of those disulfide bonds, is a critical factor in the stability of the molecule. We then wanted to compare the unfolding and refolding of the molecule in DTT to make sure that we had reversibility, as well as refolding the protein in the refold buffer, which now contains a redox pair composed of glutathione. What we can clearly see is that when we look at the unfolding and refolding in the presence of DTT versus refolding in the presence of glutathione, we do not get recovery of that I to U transition. It is still destabilized. So this was working with the native proteins. What about protein from IBs? Everyone was a little bit skeptical that we could actually do this because solubilized protein from IBs has not been through the purification process. So you could have a majority of it be your protein, but you could have some other things being carried along as well. What was really cool was that when we actually did the same experiment with the solubilized IBs and refolding in the refold buffer with glutathione, it was exactly the same unfolding reaction as it was, or refolding reaction, I apologize, as the native protein. So when we gave this information to our downstream folks, they said, it looks like the disulfide bond formation is an important issue. So they did a refolding DOE study where they looked at all those factors I had mentioned before, and they found that the correct disulfide formulation was directly linked to the refolding efficiency. They went in and they altered the ratio in the glutathione redox pair, and it had a major impact on yield. When the ratio and the process were optimized, the yield of the final refolded protein almost doubled. So this is kind of a different application of ICD, but it can be very helpful for those working with proteins that are bacterially expressed and have to be unfolded for capture. The last example is going to talk about delta G trending. And I say aggregates can run, but they cannot hide. So what was the situation? I have three molecules that are engineered to be highly similar, very, very highly similar. In an attempt to develop a platform formulation, the three molecules were placed into a standard buffer plus excipient combinations that are common to this class of protein. We performed accelerated stability testing. It was out to about 3 months. And it showed that the three molecules did not have the same stability profile. However, the majority of the assays gave results that were, let's say, subtle. So what to do? Again, I have data from other techniques that show that the molecules differ slightly in aggregation propensity and thermal stability. But to increase my understanding into the mechanism involved in these stability differences, I used the new ICD application of delta G trending. So what was done? Experiments were set up to measure the quantity and unfolding of each protein as a function of protein concentration. Proteins were measured in 2 standard formulations, and we also did some surfactant testing. So delta G trending, let me tell you about it in 60 seconds or less. Or actually, I'm going to let the experts speak. So this paper out of Ernesto Ferrer's lab, very recently published, describes the power of delta G trending. And some of the take-home things that I want you to get are this, that once a protein is made and formulated, you do have denatured protein in there, surprisingly enough, and but however, the level is extremely difficult to measure with most of the methods that we have today. You might think, well, I've got a tiny bit of denatured protein in there, but that's not going to really be a problem, right? Well, what you have to remember is that any denatured protein can aggregate, and then what it can do is it can act as a sink that will eventually deplete the native city protein. So it's almost like a nucleator, and it drives the reaction towards the denatured protein. So using delta G trending we can understand the fraction of denatured protein, the fraction of aggregated protein, and the fraction of denatured protein that is aggregated. And we do that by looking at the magnitude of the delta G. So I want to show it a little bit more simplistically because honestly this is how my mind sees how this works. So in a typical single-state unfolding reaction where you're going from the native to the unfolded and you've got no aggregation going on, both states are monomeric, there will be no protein concentration dependence on the delta G. In the second example, you have aggregation in the native state. What is going to happen is that it's going to pull the equilibrium towards the native state as you increase the protein concentration. That is actually going to show up in the fact that the delta G is actually going to increase as your protein concentration increases because it's requiring more energy to unfold the starting assembly. In the third example, you have denatured state aggregation. In this case, the equilibrium is pulled towards the unfolded state, and it manifests itself as a decrease in the delta G as the protein concentration is increasing. It's that denatured state, the aggregation of the denatured state, it acts as a sink and it pulls the equilibrium to the right, taking less energy to unfold the native form. So this is some example data from Unchained Labs ICD instrument, actually doing these experiments that I've been talking about. And this, I'm going to call this molecule 3. This is just a screenshot of the unfolding curves for the different concentrations of protein that were used. So you can see how nice the data appears, low noise, and you can clearly see that there are multiple transitions in this protein. We looked at 6 protein concentrations from 10 micrograms per mil to 1 mg per mil, and the guanidine titrations were from 0 to 5.5 molar. The instrument is in the software is so user-friendly. Once you set the baselines for each curve, the data set is then fit globally to thermodynamic models. I suggest you go back to the paper out of Ernesto Freir's lab to understand those models because they're complicated, and I'm certainly glad that there are people out there that can think like that. All right, so we're going to take a look at these 3 proteins in formulation 1 with no surfactant. So on the right is the delta G trend for the first transition. So it's basically looking at delta G as a function of concentration. What you can clearly see is that 2 of the molecules behave very similarly, and that they have a decrease in delta G as the protein concentration is increased, indicating unfolded state aggregation. And molecule number 1 shows the opposite trend. It actually increases the delta G as the protein concentration increases, showing that the native state actually is aggregated, which you would never see if you were just sitting at 1 mg per mil doing experiments. As you can see within error bars, they're all going to look highly similar. But with delta G trending, you're actually seeing there's different things going on, either in the native or the unfolded state. And then I've also listed the delta G. That simply is the delta G difference between the lowest concentration and the highest concentration protein data. Anything less than 0.3 for a delta G is not considered significant, and the program will actually tell you that there's no aggregation occurring. Now, in the second transition, again, the molecules 2 and 3 are highly similar in that they have now native state aggregation. And then the molecule number 1 shows no dependence of delta G on protein concentration. So it's not doing the same thing as the other 2 in this particular formulation. So what happens when we add surfactant? In this example, I'm just going to show you molecule 1 and molecule 3. Molecule 2 we just kind of set aside just for collecting the data and having data to share. So we decided to focus in on these 2 molecules. So what happens when we add surfactant? This is actually the first transition. So with molecule number 1, which showed native state aggregation, that continues to happen in the presence of surfactant, which there was a hope that maybe surfactant will break up that native state aggregation. Now, the delta-delta G difference is not huge, but it still indicates that in the presence of surfactant, we're actually driving the molecule more to the aggregated state. In the molecule number 3, in that first transition, remember that we had an unfolded state aggregation, and it was really, really subtle, a delta-delta G of only 0.6. However, we add surfactant, and now, again, we're driving aggregation in the native state, and the overall delta-delta G is relatively large at 3.6. We can also look at the second transition. So with molecule 1, in the absence of denature, recall that it pretty much was protein concentration independent. There actually was no sign of aggregation in the native or the unfolded state. However, the story changes when we add surfactant. We're actually now starting to see native state aggregation. And that delta-delta G of 3, even though most of it's occurring in that low protein concentration region, it still indicates that their surfactant is having a negative impact on the molecule. The same thing actually occurs with molecule number 3. In the absence of it, we did see native state aggregation. The delta-delta G was only about 1. However, in the presence of surfactant, that delta-delta G jumps to 5. So there's a major effect. Now again, if we were only looking at 1 mg per mil, which we do with a lot of assays, we would not see this impact. Absolutely not see this impact until later on down the road after the molecules have been on accelerated stability. So this delta G trending is allowing us to kind of peek into the molecule and the formulation early in the process. The last example that I want to give in this delta G trending is now comparing 2 different buffer types. The pH wasn't a big change. It was 5.5 to 6. However, the buffer species are 2 different ones, so we'll keep that in mind. So this is looking at the first molecule and the 2 different buffers. So on the left-hand side is the first transition, right-hand side is the second transition. So that first transition, we still are seeing native state aggregation in the presence of the alternative buffer. So the blue is the data that I showed you before. The red is the alternative buffer at pH 6. It absolutely is magnifying that aggregation of the native state. I sound like I'm repeating myself, but again, look at 1 mg per mil. If I did this experiment at 1 mg per mil, I would say, wow, look at that. I have a delta G1 of 9 kilocalories per mole versus 5 in buffer 1. Buffer 2 is the way to go. But you have to look at the trend. The trend tells you, no, you need to think about this, because even though at 1 mg per mil it appears to be more stable, there's something else going on behind the scenes. With the second transition, really not as much of an effect, although we did start to see a little bit of native state aggregation, but the overall delta-delta G was less than 1. How about the second molecule, molecule 3? Well, even more of an impact. It was major. For molecule number 3, in the original buffer that I showed you before, remember we had unfolded state aggregation, really small delta-delta G. However, in the presence of this alternate buffer at pH 6, we get a huge dependence on protein concentration. The delta-delta G is pushing 10, which is a lot. 10 kilocalories per mole is a lot. And then in the second transition, we see a similar case, not to the same magnitude, but still quite large at almost 6, a delta-delta G of 6. So again, if I was looking at 1 mg per mil, I would pick buffer 2 right off the bat and say this protein is so much more stable in this pH 6 buffer than it is in the pH 5.5. So let's go with that buffer. But again, we kind of have to look behind the scenes and see what's going on, and delta G trending is allowing us to do that. So overall delta G trending, I honestly see it as being very illuminating. For most of our biophysical assays, the working protein concentration is usually around a half a mg per mil to 2 mg per mil. But as we had seen in the examples of the 3 molecules in the same buffer, if we just looked at the transition at 1 mg per mil, all molecules appeared equivalent. And then if we looked at the second transition, there was a slight difference, a small protein concentration dependence versus none. So it really, really is a balance. I also want to highlight the fact that fluorescence measurements are highly sensitive, so it allows the experiments to be performed at low protein concentrations outside of the sensitivity range for other methodologies. This delta G trending and this concentration effect, the magnitude of them, and it's amazing because they're actually highlighting where the aggregation is occurring, and it's an important factor not only for formulation development, but you can imagine this can be leveraged in other areas such as purification development and candidate selection. So what do the experts say? Definitely want to go back to the paper out of Ernesto Ferrer's lab, where it states that the engineering goal, whether it's candidate selection or formulation, is that you want to pick conditions that maximize delta G, but simultaneously minimize its concentration dependence. So we have to be really careful about not picking the highest delta G based on our higher concentration data, and also looking at the concentration dependence. And we've got to find middle ground. We may never find a point in which we get both maximized delta G and no concentration dependence, which would be the best case scenario, but we have to look for that middle ground. What now? After seeing this data, I feel like I've got so much more insight into what's going on with the molecules that I have shown data for today. And I really think that ICD and this delta G trending is providing a lot of additional data that we can leverage early in a development program, whether it be formulation development, candidate selection, downstream processing development, all of those things. But as a scientist, going forward, it's going to be important for me to understand how to integrate these results with data from other assays. I don't want to rely just on one assay, as I had indicated before, because we always want to strive for scientifically driven, rational development when we're developing stable protein therapeutics that are one day going to be given to humans to fight serious diseases. So I have to figure out where in my development programs that ICD is going to fit in, and I actually right now feel like there's several places, definitely early in the program, and then maybe as a spot check throughout the program as the molecules go on accelerated stability. With that, I'd like to thank you so much for your attention and joining us today. I would also like to thank my colleagues at FUJIFILM Diosynth Biotechnologies, Greg Adams and Phil Ropp, as well as my friends at Unchained Labs, especially Brian Lightbody, Rick Brown, Patrick Ross, and Paul Kersley. And finally, I would like to thank Ernesto Ferrer, who, after almost 20 years, still makes isothermal chemical denaturation for me a lot of fun. With that, I say thank you, and John, back to you.
Thank you, Catherine, and thanks again to you, Joe, for your timely presentations on stability determination for protein comparability and for formulation optimization. You both covered quite a lot of ground, so thank you. Hey, it also looks like you struck a chord with our audience as we received some very interesting questions for our Q&A session, so why don't we take the first one. Okay, so first question is for Catherine. On slide 60 and 61, what were the surfactants that caused the increased aggregation and why?
This is a common surfactant used in protein formulations, polysorbate. Polysorbate can help and it can hinder at the same time. Being a detergent, it can facilitate partial unfolding of the molecule, so that would be its negative part. But the positive part is that it can also kind of impede hydrophobic surfaces from interacting, thus blocking aggregation. It just really depends on the protein. But to answer the question, it's very common polysorbate.
Thank you. And Catherine, how sensitive is ICD for more complex substances such as viruses, where the activity of the product might be lost due to subtle conformational changes in a few critical proteins, even when the variant as a whole is largely unchanged?
I think it all depends on the magnitude of those subtle conformational changes in your delta G or delta Gs if you have multiple transitions, which I'm assuming you probably would in a case like this. So it just all depends on how those areas of the protein are contributing to the overall stability of the viron, and it would just have to be an experiment that you would have to just test and see.
Okay, thank you. And Catherine, can you comment on the use of ICD in comparability assessment? How is it used in comparability, and how often is it used in comparing lots from different manufacturers and biosimilars?
I think it's really a method that's set up to do exactly that, comparability assessment. If you're doing the experiments well, the instrument is very reproducible. So as Joe said earlier, even changes as small as 0.1 kilocalories per mole can be detected. So I think ICD in of itself and doing chemical denaturation, even without the delta G trending, is very useful in comparability assessment. I am definitely a person who likes a holistic approach, so ICD for me would be part of the package. In terms of delta G trending, I think it could also be used in a comparability assessment just to make sure that the molecules are behaving. If there's an aggregation issue, it's happening in the same state to the same magnitude.
Joe, does the HUNK system predict aggregation for complex products such as viral vectors?
So we haven't specifically tested viral vectors, but we have looked at proteins that are any sort of protein besides, including monoclonal antibodies. Anything that has a tryptophan or some tryptophans that are going to change its state during denaturation can be monitored easily with a HUNK.
And Joe, what's the concentration range for the HUNK?
It's in the low micrograms per mil, so a monoclonal antibody can be tested. I think the lower limit we've tested is about 3 micrograms per mil, up to about 100 mg per mil. You don't have to work in that higher range to get the delta G values, though.
Okay. And Catherine, does my protein have to unfold reversibly in denaturant, for example, guanidine, HCl, or urea, in order to use the delta G trending application?
It does, actually. So remember early in my presentation, we talked about how the delta G in the absence of denaturant was actually calculated. And it really is all based on the fact that you're reaching an equilibrium as a function of denaturant concentration so that you can calculate KEQ and therefore calculate delta G. And it's simple thermodynamics. As long as that you have a reversible reaction, using the thermodynamic parameters is valid.
And Catherine, is prior ICD experience necessary or advised in order to be able to run the instrument?
No, not to run the instrument. It's pretty straightforward to set up. I think where it really comes into play is interpreting your data. It's not, unfolding by chemical denaturation is not particularly complicated, but when it comes to delta G trending, just really understanding what the data is telling you, prior experience can be helpful, but running the instrument is the instrument makes it easy.
Great. And do I need to know complex equations to fit and interpret my data?
Again, it's one of those things where it's a nice to have if you can understand what the fitting program is actually doing. But thanks to Unchained Labs and Ernesto Ferrier, they have built the software with those complex equations. So, it really is very nice within just a couple of seconds to get the fit of your data. So again, knowing them is great, but definitely not required.
And Joe, can HUNK be used with smaller proteins for delta G measurements?
Yes, as long as there's a way to monitor the unfolding by fluorescence, There's no size limitation on lower limit of the size limitation on the HUNK.
And Joe, the tray shows 96 well blocks. Are there other ways to use larger formulation volumes?
Yes, so that particular example is for formulation screening. There's 5 different trays that will have different configurations depending on if you have either you're screening multiple proteins or protein constructs versus 1 or 2 formulations, or if you're screening multiple formulations against 1 or 2 proteins, or if you're auto-formulating on the fly.
Joe, thank you very much, but unfortunately we've run out of time. Please note that this webinar will be archived for 6 months on our website, www.genengnews.com. If you miss parts of it, you can watch it again, or you can recommend it to your colleagues and friends, which we highly recommend. Thanks again to the panel for their outstanding presentations, and I want to say thank you to our audience for your attention and for your thoughtful questions. And thank you to Unchained Labs who made this webinar possible. Bye-bye for now.